I guess, should we start with online questions? No? We know. Okay. Okay. Do we have questions from the audience?
So I got I guess, more directed to Jonathan and maybe Sarah as well. But in terms of high temperature data, in addition to what's already known in like high temp line lists and whatnot, how complex can molecules get with high temperature simultaneously detectable with JWST?
Oh yeah, with the face talking. So high temp is this high temperature line list run out of, and it's good, but it's actually extremely incomplete.
Sure.
But in all likelihood, the molecules that we'll be able to see with James Webb are the ones that are really the most abundant.
Mm-hmm.
So it's things like water vapor, CO, CO2, methane, sodium and potassium, which is weird, but they're pretty abundant and they have very strong absorption lines. There's some hydrides like FEH, which is not a molecule we ever really deal with, but in the hydrogen-dominated atmosphere. So it's really those things that have features in the infrared, and then also are just kind of cosmically relatively abundant. So the kind of the CNO-dominated molecules, but relatively smaller ones. Although that being said, we don't have any of these spectra yet. So
Sure. Yeah.
I could say, oh, it's probably going to be this, but I'll be wrong, right? So, so those are the things I would think of. But
Yeah. But like, so I mean, for example, Peter Brunath's measured ethane up to 3,000 Kelvin or whatever it is.
Mm-hmm.
Do you anticipate it getting any more complicated than ethane, or is ethane something that's already going to be pushing the JWST limit of detection?
I mean, it'll depend on the abundances,
Okay.
and I have no confidence I could guess for how abundant. Certainly, those things are seen in the outer solar system in relative abundances, and we can see them. Yeah.
Other questions?
How come they haven't put a telescope on the moon? I'm just curious in terms of the relative advantages of, having one in orbit versus having one sort of just sitting there.
I feel like that might be above our pay grade.
Well, no. I mean, I'm just curious because, right? I mean, they land rovers, right? They send rovers to Mars and so forth. So you could imagine they could, kind of plunk something down there. So I'm just kind of curious, because a lot like when they talk about launching James Webb and stuff, right? Those sort of stay in orbit. I was just kind of.
Stephanie's really dying to answer here.
This is one of my favorite questions. It depends on what kind of telescope you want, first of all. Second of all, the moon goes around the Earth. So putting something like an infrared telescope on the moon, on the backside of the moon, you're going to have the sun in your field of view most of the time warming up your telescope. This is why we're putting James Webb 1 million miles away from the sun so it doesn't warm up. If you want to do something like a radio telescope, that would be a more interesting prospect. So something like ALMA on the moon. And this is something a lot of people actually are talking about. But again, your field of view is going to be inhibited by the sun for some period of time. We deal with this with things like Hubble, so it's something that we can do. It's just there's not too much to gain, especially at radio wavelengths, because we can already see through most of our atmosphere. So it's telescopes that we can't see through our atmosphere where we gain the most. But again, putting an infrared telescope on the moon just doesn't make much sense.
It would also be a lot of mass to put ALMA on the moon. So you'd really need to be able to use the resources there and, more wild speculation. 3D print yourself. That's what I was going to say. You need to 3D print the dishes. I would be completely supporting of that effort.
Yeah, you
Especially
also
for
need
water.
the Space Launch System, right? That's step one, right? To have a big rocket. Right now we're paying Russia to send astronauts up to the space station, right?
And an orbiter to send the data back. Because if you do put it on the opposite side of the moon, you can't really communicate with it. So then you'd have to also have this continuous orbiting system. Obviously, we all enjoy thinking about this, though.
I would however really like to build my lab on the moon because Earth's atmosphere is like the worst nightmare for the work that I do. So if anybody wants to build something to make science better on the moon, my lab would be a great thing to put there.
With you.
Sure, why not? And I think most of my grad students would be amenable to coming also. I can't speak for them right now because they're not here, but that sounds like them.
All right, Glenn.
The mass spectrometer data and sort of, so the chemistry on Titan now, is that similar to the chemistry on the Earth a few billion years ago, or is that completely irrelevant?
That's a really hard question to answer because we don't. Well, first it depends on which part of early Earth's history you're talking about. The further back in time we go in Earth's history, the less we actually know about what was going on with its atmosphere at all, to the point that we don't even know things like atmospheric pressure, for example. We do think that there was probably a period of Earth's history where similar chemistry was going on, although the temperature was never as low as it is on Titan, and that has a lot of implications for what chemical processes might be happening, in particular what molecules would be stable, which pathways would be favorable, things like that. There's some evidence that there may have been a global haze layer at some point in Earth's history, and so that's something else to consider, but it's a really hard question to answer. I always joke, well, we don't have a time machine, we have a spacecraft, we can go study some of these processes, but at the end of the day, we don't actually know what Earth's atmospheric composition was like, and there's a lot of people who are working to answer that. If we could get some more constraints with the modeling abilities that we've developed from studying Titan, I think that we could get a better understanding of what else might have been in Earth's atmosphere at that time, but it's really hard.
Chemistry that we are seeing in the mass spectrometer showing, gazillion atomic mass unit molecules, is that all formed in situ, or is that thought to have been deposited? So where is that coming from?
For Titan, we think that most of the chemistry is happening there, although there's still a lot of questions about the role of an external input in terms of the kind of chemistry that can happen. So things like these oxygen ions, there's other stuff flowing into the atmosphere as well. For Saturn, the very last slide that I showed, that is like, nobody knows what's going on with those data right now. And so it's really unclear. Some of that material is very, very clearly coming from the rings. We know that. But there's a big question, especially with the heavier ions, about what fraction of those might be coming from the rings, what fraction might be coming from chemistry in Saturn's atmosphere, what fraction might be coming from contamination or chemistry within the instrument, because at that point in the mission, Cassini was going 30 kilometers a second. The mass spectrometer was designed to operate at 6 kilometers a second. Those are very, very different velocities when you have ions crashing into the inlet of your instrument. And so for Saturn, we don't really know, but we do know some fraction comes from the rings. And so, again, both of those atmospheres have an external input that's really affecting the chemistry, and I think that's an important life lesson.
Question for you. Your foray into ChemDraw, I couldn't see it very well, but it didn't look like you didn't have any heteroatoms there, yet the atmosphere is dominated by nitrogen. Is that insightful, or just because you couldn't figure out how to do nitrogen in ChemDraw?
There were, if you look closely, there were a couple of heteroatoms. Again, that's not a real molecule. Although I will say, I mentioned that a lot of the Titan molecules, the detections that I showed you, were all from calibration data. We have other ALMA data. There have been a handful of ALMA proposals that have been actually selected to study Titan. Most of those so far have not found any new molecules. We have some good upper limits now on some sulfur-bearing compounds, on a couple of other water-bearing species, and there was a proposal that was selected to look for nitrogen heterocycles. Unfortunately, I know what the outcome of that proposal was, but I don't know if it's public or not. And yeah, okay, Stephanie is shaking her head no at me. But that is something that is like the very, very most obvious next thing to look for, given what we now know about the chemistry, is to look for nitrogen heterocycles, and we're doing it with the only tool that we actually have available to us at this point, which is ALMA.
But that wouldn't show these massive. I mean, you were out huge, right?
Yeah. No, the only way we're going to get the really heavy stuff is with another mission. Unfortunately or fortunately, depending on what happens next spring.
More questions?
So if I wanted to build a model, right, there was this call essentially for laboratory simulation of atmospheres on other planets. Am I ultimately going to come up against this wall of a limit of a testable hypothesis because we will just not be able to physically go to those places, with a few exceptions from return missions and so on? Ultimately, how does one deal in this field with the reality of not being able to go and verify, but being stuck with, for really 99% of the data, with remote observations and interpretation of line shapes and so on?
That's a great question. I mean, when modern solar system planetary science kind of got started in the 50s and 60s, you had meteorites, you had telescopes, and that's all folks had for a few decades. One of the things that I sometimes show in talks is a spectrum of Jupiter from 1969, and that was the first mid-infrared spectrum of Jupiter ever taken. And everything you could infer about Jupiter from that spectrum has stood the test of time. Those things were all true in terms of Jupiter's, what its main absorber was, how deeply we could see as a function of pressure, that you could actually tell that Jupiter had a stratosphere, it has a temperature inversion, all those things you could tell from a really crude spectrum. And so, to me, I always try to be mindful about the level of question I want to be able to ask and answer in the exoplanet context. And as someone who does solar system stuff too, I try to jump back and forth. And I think a lot of people, aren't mindful of that, in that there are people who can really run really sophisticated models that really aren't going to be testable in our lifetimes, or perhaps ever. And so I think you just have to ask the appropriate question and think about the data that would need to answer that question.
Follow up. Then does the field limit itself in terms of the insight that it gains by staying in the box of Karl Popper's way of doing science, the scientific method? Or is this actually an opportunity to go out and say, you know what, we got to also come up with models that may not be testable in our lifetime, and maybe that's a good thing? Is there a discourse about that or dialogue in the field?
I think stuff like that happens all the time in the solar system, and that's just part of doing business. I wouldn't say it's, maybe I came across a little negative. I wouldn't say it's all that frowned upon. In that sometimes running models and having multiple people running models that get a consistent answer, that often can serve as some sort of replacement for having data to verify if everyone, if there's a variety of different modeling techniques that all kind of arrive at the same answer, that can be established as what probably is going on.
Yeah, I think it's in the terrestrial world, there's no doubt that 1,000 flowers are blooming, and lots of people are, trying to think of ways we could detect, plants and chlorophyll and various other things that are never going to be in our capability for, 50 years. So that is happening. But there's another aspect, right? So everything that you're talking about, these aerosols and various things, they come from somewhere, right? The base constituents. So, Jonathan said that we can maybe see FEH, right? Well, if you don't see FEH, maybe that's perhaps information that iron is not there. Maybe all the iron's in the core, right? Where if it's core accretion. So maybe you can start to rule out other things. If you have carbonaceous haze, methane's much better at that than is CO or CO2. right? Because if oxygen's there, it just gobbles everything up and it goes back to CO or CO2. And so there's other ways to approach this from the base constituents, and I think that's where we are now. And frankly, I think it's amazingly, it's awesome. Yeah.
20 years ago, we barely knew anything about discs, and now Alma is giving us almost daily surprises about the chemistry of a disc. So, yeah. I
mean, just to add on that, what's amazing is that all these astrochemical models we use, they were trained on molecular clouds, and we've seen, I kind of, in talks, you focus on like the problems, and it makes a better story anyway. But I mean, in many ways, there have been so many amazing successes of the models in this new regime where the radiation field is a lot stronger, the densities are a lot higher. I mean, maybe they're closer to PDRs, but regardless, I think there have been a lot of amazing successes in these models, and they were developed before we ever dreamed of making molecular maps and disks.
Question in the back.
This one, okay. So Ted gave us a really good talk on the factors that contribute to carbon delivery to planets, and in the subsequent talks we heard that Earth and Venus and Titan have very nitrogen-rich atmospheres, and so I was wondering if any of you have thoughts on what controls the delivery of nitrogen to terrestrial planets, and whether or not we can assume that that happens to terrestrial exoplanets. Like if I were to build a photochemical model of TRAPPIST-1 planets, how much nitrogen should I assume is there?
Sure. That paper that I was talking about was actually carbon and nitrogen. I just threw nitrogen off the board for time constraints. Nitrogen is an order of magnitude more depleted in the Earth than is carbon. So as bad as carbon is, nitrogen's worse. Nitrogen is rarely found in abundance in cometary material. And so that really suggests that nitrogen was in the gas not only in the inner solar system like carbon, but in parts of the outer solar system. So it's a lot harder for nitrogen to be there. But, Titan has probably an awful lot of N2. Pluto does. And so you could imagine, that there will be an N2 ice line. And if bodies form beyond that N2 ice line, they would be super nitrogen rich. But on the Earth, we think the carbon to nitrogen ratio is maybe in a way telling us something about the origin of how our planet was born, and that it was highly likely the planet was born with an awful lot of nitrogen in the atmosphere that was lost via impact ablation. But that's really just speculation at present.
Other questions? Amanda.
Okay, this is a question for Jonathan. On your slide where we were looking at the young, cool Earth paradox, there's a downslope going back in time for temperature, but then at some point there's also the upslope for when we were molten. Do you want to comment on why we shouldn't worry about that upslope and assume that that solves the young, early Earth paradox?
That young, really hot molten phase. I'm no geologist, but my impression is that that's supposed to have lasted 10 to 100 million years, and then your planet has cooled off, and at that point you still have some energy coming out of the interior. You have a little bit of radioactive decay, but you're really dominated by, in terms of the energy budget, by what you're getting from the sun. And so it's just that cooling phase after you're a molten rock is just quite fast.
There's another aspect, right? Because we call it a secondary atmosphere, because the original atmosphere was probably H2 captured from the nebula very weakly, and that was lost over time. So how long you kept that H2 could also influence this evolution.
Yep.
Other questions for the panelists? Yeah.
Sorry, I have one more. With water being so important, and it being a complicated molecule that can be photolyzed and so on, is there an estimate that's reliable for how many moles of water there is in a I don't know, the universe, that's probably a bad, poorly formulated question, but let's say in our galaxy, or, you know, percent-wise compared to all the other
We don't work in moles.
I know there's 10 to the
Sorry,
46
we've
on
lost
this
that,
planet.
that wrote. From what it looks like in the chemistry that starts everything off, all roads lead to CO and water ice. So the oxygen that's free, that's not in silicates, is going to water ice. So there's basically that's it. All the oxygen in the galaxy is either in silicates, water ice, or CO. And the reason why the Earth is so water poor, it's what I think 0.2% or 0.02% by mass, is because the Earth formed inside of the water ice line. So, you know, it suggests that anything formed beyond that point would just be a water world. Yeah, so I think it's an expectation value in a way. We're missing 10%. It may be in really fluffy grains, but yeah, 30-30-30 is about right.
Other questions? All right, I think we'll wrap up here so Ted can catch his flight. Thank you all for coming. It's been a great day.